Alright, so we are doing this exercise. And so basically, yeah, we're just dealing with random variables and trying to prove this thing. So, just as a reminder, in this exercise, let's be clear of where these functions are living. So x and y are functions which map from a probability space omega to R, and f goes from R to R. Yes, that is an airplane at a hotel near an airport. It'll happen. Alright, so if there exists a measurable function f such that y equals f of x, then y is measurable from x inverse of the Borel sigma algebra on R to R, measurable. And this is just, let's see here, I think it's this theorem. It's essentially compositions of measurable functions are measurable. And so, the collection of x inverse R to R measurable functions contains the collection of all functions of the form f of x where f is measurable. So this is what we're trying to prove. We're trying to prove that these functions, that these two classes of functions are the same. The one on the left is the class of functions which are measurable with respect to sigma x, because recall this is the definition of being measurable with respect to sigma x. And the class of functions on the right are the ones which are of the form y equals f of x, where f is measurable from R to R. Okay, so we've proven one inclusion, and we need the other inclusion for this exercise. And if we look at this exercise, it says use the previous exercise to conclude blah, blah, blah. And we haven't used the previous exercise, so we probably should. For the reverse inclusion, let phi be a simple function with respect to x inverse R, i.e., okay, so what are we going to do? We want to show that the collection of measurable functions here, let's just start doing it and we'll get there. Okay, so let phi be a simple function. So what this means is that there are real numbers c1 through cn, and there exist sets a1 through an in x inverse Borel sigma algebra R, and these ai's are disjoint, and these things satisfy phi is just the sum from 1 to n of ci times the indicator function on ai. Now for any particular I, since ai is in x inverse of R, we know that there is some set bi which is in R such that x of omega is in bi for all omega in ai, because that's what it means to be that's what it means to be a set which is in the inverse image of R. Basically that means that there is some set in the Borel sigma algebra on R such that x inverse of, so essentially what I'm saying here is that x inverse of bi is precisely AI. And that's the same thing as saying that for all omega in AI, x of omega is in BI. Alright, so now the BI's are disjoint. Because if there exists an omega such that x of omega is in BI and BJ for some I and j which are not equal, well, no. Let's do it this way. If there exists an omega such that x of omega is in both BI and BJ for any I and j, then omega must be in both AI and AJ. Because omega must be in AI in order to map to BI under X, and omega must be in AJ in order to map to BJ under X. But the AIs are disjoint. So the only way that this is possible is if I equals j. Therefore, the BIs are disjoint. Alright, so note that if omega is in AI, then x of omega is in BI, and so f of x of omega is precisely CI. Thus, f of x equals the sum from 1 to n of CI indicator of AI, which is precisely phi. This shows that a set of functions of the form f of x, where f is measurable, contains all simple functions. Alright, so what did we do here? We took this simple function phi and wrote it in the form f of x, where x is the function, the random variable that we're given, and f is a measurable function. Well, what exactly is f here? It's not entirely clear to me what f is and why it is measurable. I think f needs to be to involve the BIs. Okay, this is really risky because I'm pretty tired at this point, but I really have to go through and sort of fix this. X of omega, so f. So if omega is in AI, then x of omega is in BI. So f needs to send elements of BI to CI. So f think f of just a real number y is going to be the sum from 1 to n of ci times the indicator of AI. No, of BI. Does this make sense? Does this make sense? Yes, because x is just whatever random variable we were given, and f here is a measurable function because it is a simple function. And the BI's are elements in where? These are Borel functions. These are Borel sets, right? I said that already, right? Yeah. There exists a BI in R such that x of omega is in BI for all blah 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 blah. Okay. So this should really say, thus f of x equals this thing. What it really should say is this. If f of y is defined in this way, let's make it a little smaller. Let's try to squish it in here. If f of y equals this thing, then omega is in here, blah, 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 blah. Now we can move this up. And there we go. Right. Okay. So basically we had to do this whole tricky, well, it's not really that tricky. I'm just pretty tired. But we had to do this whole thing to prove that the set of, to take any simple function and write it in the form f of x. We had to figure out what f was, and the way we figured out what f was is we took all the sets in our simple function phi, and we took their inverse image under x, and took those, no. Yeah, we took those. No, we took these sets A, and we figured out which sets in R would pull back to these sets, and those are the sets that we used. Okay, and then we used that to construct a simple function, and then we were good to go. Okay, so cool. So we've done part of this. So the set of functions of the form f of x, such that f is measurable, it contains all simple functions. Now, if we want to apply the previous exercise, what's the next thing we're going to need? We're going to need to prove convergence under pointwise limits. And then what will that prove? That will prove that this contains all measurable functions. And when I say measurable, I mean measurable from x inverse of r to r. And that's exactly the class of functions that we want to... Wait, that's going to prove that the set of functions of the form f of x, where f is measurable, it contains all x inverse r to r measurable functions, which is exactly what we're trying to prove. All right, so let's wrap this up. Let's get convergence under pointwise limits. For convergence under pointwise limits, or closure, whatever you want to call it, let Fn be measurable such that, and these are measurable functions from R to R, such that there exists a y such that Fn of x converges to y pointwise. So what does this mean? This means for all omega in our larger space omega, the limit as n goes to infinity of fn of x of omega exists and is precisely y of omega. Now we're going to define f of, let's call it f of z, to be, now here we're going to write lim sup as n goes to infinity of fn of x. No, z. I'm using z here because we're using x too much. Okay, and why are we using lim sup? I don't think it's absolutely necessary, but it might be necessary if you're being very technical, because note that the limit as n goes to infinity of fn of z exists necessarily only on x of omega. So I think this is the issue. This is why we use lim sup, is because we know that fn of x converges pointwise to something which is called y. That's just how we define y. We define y at every point to be the pointwise limit. But this only really applies to points in let's see here. Well, wait, this limit only exists necessarily. So we take a real value, so f of z is this lim sup of this thing. Right. So this limit as n goes to infinity of fn of x of omega, this will only necessarily be defined, the domain of this function is x of omega, which is certainly a subset of R, since x maps into R, but it might not be all of R. And so if we just define the limit as n goes, if we define y to be, if we define f to be the limit as n goes to infinity of fn of z, then this doesn't necessarily, there's some issues on the real line. There could be some issues. There could be some places where we don't really know what happens because f isn't really defined there. I guess you still have issues there anyways because it's still not really defined there, but at least if we use lim sup, we know that the limit always exists. Lim sup always exists. Limit doesn't always exist. And so here we're just being safe. Or there is a more important reason that I'm not remembering right now. So anyways, let's continue. Since the fn's are measurable, and again this is measurable from x inverse of r to r, so is f. And that's because we've proven that a lim sup of random variables is also a random variable. Furthermore, for all omega in our space omega, y of omega equals the limit as n goes to infinity of fn x of omega. And so this certainly, on the set where this is defined, it's certainly going to equal the lim sup as n goes to infinity of fn of x of omega, which is precisely f of x of omega. And so y equals f of x. Right, so there we go. Thus, fx, where f is measurable, contains all simple functions with respect to, and simple with respect to x inverse r, so these simple functions, the indicator functions, are sets which belong to x inverse r, and is closed under pointwise limits. And thus, by exercise 1.3.7, the set of functions f of x where f is measurable contains the set of functions of the set of x inverse r are measurable functions. Hence, these two classes of functions are equal because we've proven by inclusion. And so yeah, this is a little bit tricky, but really all we're doing here is we've really done a lot of the work already in the previous exercise, and we're just applying it here. And so we did have to do a little work to show, we did have to take a little bit of time to figure out how to construct an f which guarantees that this class of functions of the form f of x contains simple functions. But after that, the closure under pointwise limits was actually pretty straightforward because we just applied limits, the fact that limits of random variables are random variables. And then everything just sort of followed from there. Then of course the other inclusion was pretty easy to take care of, and so we got this nice relation, and so these two sets are the same thing. And so yeah, I guess measurability can sort of behave somewhat nicely with composition of functions in this particular way, and we're done with the exercise.